Last time when we introduced the multiplication of matrices, I told you that multiplication, say if you model things from numbers, they have this, there is a special number there, which is we call the 1, which has this property, you multiply by any other number, you end up with the same number. And we build up the analogous element in the matrix scope, which was the identity matrix. Now, with the multiplication with numbers, there's another property there, which we call the inverse number, right? Every number besides 0, has an inverse coupled to it. And the property of this inverse is like this, right? I model this on matrices now. If I have a square matrix, it's a good question to ask now. Do we have an element which is square matrix? And I put a question mark here because we don't know the answer to that yet. Do I have a matrix with the property that if I multiply my A with this matrix from left or from right, and this time I have to make this distinction because multiplication is not commutative, and the result of that will be the identity. If we have such a matrix, if we do have such a matrix X, this X deserves a name, the inverse. And that's if we have it, we will call this X the inverse of A. The question is, do we have it? No, it's not the right answer. And the answer no also will not be the right answer. The answer will be it depends. It depends on it. Unlike numbers, with numbers it's easier. It's non-zero, we have the inverse. Unlike numbers, with matrices, the equation is much more like the study of this, the answer yes or no. The answer to that is rather more, well, it's more complex than with numbers. And that's something we're going to look at right now. How do we see how we can see from this matrix itself if we can produce an inverse or find an inverse with this property? I'll give you some insight into this. If you first look at this question, I'll start with the example. I'll take the example like this. It's the example on page 14. And it looks at the matrix like this. 1, 2, 3, 2, 5, 3 is 1, 0, 8. Yes, and I'll try to address this question about whether this matrix has an inverse, whether my matrix has something like this. I'll try to see on this particular example, and I'll give you some guiding remarks in relation to that. So if we're looking for this inverse, if I was looking for this inverse, so if I was looking for something which makes this happening, of course I would look at this x as sort of unknown, right? We're looking for this x. This is the unknown. This time this is the unknown which has it's not a number. It's a matrix. It's a matrix of the suitable size. This time it's a size 3 times 3. So in fact we'll have 9 unknowns, right? 9 entries of this unknown matrix X. So actually I put it here. All of these unknowns here they are. All 9 of them, and our job is to find them. Simply spoken, if I make some shortcuts, you can think about this way. Essentially, if you just take this matrix, if you plug it in here, if you sub in, and if you do the matrix multiplication, you do the matrix the way you do the matrix multiplication, and then you equate the result on the left-hand side to the result on the right-hand side in the entry-wise fashion, you will end up with 9 equations with 9 unknowns. Right? Do you see that? I mean, like, you don't have to do that. We're not going to do that. Don't get it's a huge thing to do. We're not going to do that. But in principle, if I sub in x in here with all of these unknown components, if I sub in a in here with all of these known components, if I do the multiplication the way I do multiplication with matrices, there will be some expressions, long one, involving all of these unknowns. If I equate to the elements here, and I know the components of this matrix too, right? It's 1, 1, 1 on diagonal, 0 the rest. There will be some equations, and in principle, we can solve them. That's what we're going to do, in fact, but we will do it in a structured way, in a way, not like this direct way. Look at this, what I'm going to do. I'll give a name to the columns in this matrix. So the first column will be x1, the second will be x2, and the last will be x3. Because when you do it in a structured way, it gives you much more insight into what's happening, and it gives you also the idea how to do it effectively on every particular example. So I'll give columns to this matrix. So in the column 4, my matrix is like this: column number 1, column number 2, column number 3. They're still unknowns, but we'll try to do it not in the per component form. We will do it in the vector form. Now the main thing which I need here, and it's something I'll probably ask you to believe me, you can check this. it's like algebraic identity. It is like this. It says if I have a matrix A, and if I multiply this matrix by the other matrix, which is structured like this, which have columns in it, so it's the same matrix X, I just write it differently. I wrote it with the column representation like this. If I do multiplication, the way I do multiplication, the result of that will be matrix. If I structure this result in the column form, it will be like this, where every individual column here, this is a column, this is a column, and this is a column. Every individual column here is the normal matrix multiplication of this A with this 3 times 1 matrix, with this column as a single out matrix. This is the algebraic relation. This is a property of the matrix multiplication alone. It's a useful property. Some of the questions in yellow book, you can, if you know this, you can work them out in a much easier, nicer way. Remember this. It's one of the properties of the multiplication. If I multiply a matrix A with something like it's another matrix, but if I structure it like columns, the result will be again structured like columns, and every individual column will be like individual multiplication A with the each column here. Now, if I use this property here, if I just look at this left-hand side in this fashion, then I will have this, right? So I have something like this. If I look at this identity, if I start with this identity like this, so I have something like this, AX times identity. Here's my identity matrix of size 3. In this matrix, I will also name the columns. And that will be the name for the columns here. I don't know if you remember this bold-faced E, we use this for the standard basis vectors, and in fact these are standard basis vectors in R3. So think about this. Left-hand side, that's the column structure of the left-hand side. Right-hand side, that's the column structure of the right-hand side. So if I now equate this everything in the per column way, so that's the left-hand side structure, that's the left-hand side in the column structure, that's the right-hand side in the column structure. I will equate now this to this, well, per column way, this column, second column to the second column, last column to the last column. If I do that, I will have 3 systems of linear equations, right? Because this is a system of linear equations. This is a system of linear equations. This is a system of linear equations. If you remember what I said at the beginning of the question, I said if you sub everything in, you will end up with the 9 equations with 9 unknowns. Here they are. 3 equations here, 3 equations here, 3 equations here. Altogether 9 equations. I just keep them separate because it's easier to analyze them separately. Good. Now, when you look at the system of linear equations, how do we solve it now, these days, especially after last week? We do row. Sorry, I didn't catch that. Say again, please. Guess and check. Guess and check. Yeah, well, you can do that too, yes. But not in this case. Yeah. If your guess and check failed, then the second alternative for you will be row echelon form. So you have to extract the augmented matrix for each of the systems, and if I do that, this will be the augmented matrix associated with my first system. This will be the augmented matrix associated with my second system, and that will be the augmented matrix associated with my last system. Now, each of them I have to solve. Each of them share the same left-hand side. So before I will move on with the solution, before I move on to the row echelon form, I make one extra assumption now, and that will be the key assumption to the whole finding the inverse process. You will realize it in a second. I'll make this one single assumption. I'll make the assumption that if I take the left-hand side of my matrix, and if by some clever way I'll convert this left-hand side to the reduced row echelon form, each particular matrix will have its own set of elementary row operations, which will take this matrix to the reduced row echelon form. You can do it with any matrix, but the assumption is, which I will make, is that this result, this reduced row echelon form, it will have every column leading. That's a kind of extra assumption I just now throw into this mix. And I want to ask you the question now. If you have a matrix, 3 times 3 matrix, which is the reduced row echelon form. Try to imagine now it is in your head. You have 3 times 3 matrix, which is the reduced row echelon form. What kind of matrix it is? It's the only option for such a matrix, with the free leading columns, sorry, that's the other thing which I have to say. If the reduced 3 times 3 matrix, which is a reduced row echelon form, and which has every column leading, it's only one option for such matrix, because every pivot must be unity and must be zeros below and above the pivots. So this matrix must be the identity. That's the only option for such matrix. So that's the kind of assumption we're looking at. We assume that the A matrix is the one which goes into the identity after you do the reduced row echelon form on it. Now I can do my reduced row echelon forms on these 3 augmented matrices. If I do the same set of row echelon form operations, which are here, which I needed to convert my A to identity, the reduced row echelon form of this matrix will be something like this, with some right-hand side. You do your operations, left-hand side will go into identity, right-hand side will go into something. And I call this something B1 vector. If I do the same set of reduced row echelon form operations on this matrix, it will be this result, and on this one will be something like this. Every time you will have something else on the right-hand side, and every time you will have identity on the left-hand side. Now, if you do back substitution in a matrix like this, so that's your unknowns here, right? X1 was the unknown here, X2 was the unknown here, X3 vector was the unknown here. If you do the back substitution in a matrix like this with the identity on the left-hand side, the back substitution will take you right down here. That would be the solution to this system. That would be the solution to this system. And that would be the solution to this system. That's how we do back substitution. When your matrix is, when your left-hand side is in a reduced row echelon form, and every column is a leading one. But remember, x1, x2, x3, they were columns of my unknown inverse. So the columns of my, here's the strategy now for us. All this discussion just open up the strategy for us. All we have to do, we have to write my A matrix, the one we go after inverse, for which we're looking for the inverse. We have to construct these 3 augmented matrices with the standard basis vectors as the right-hand side. We have to convert them to the reduced row echelon forms, and we have to collect the appearing right-hand sides as the columns of my inverse. This is the strategy how to find the inverse, and this will always work as long as you meet this requirement. Now, in practice, if you try to do this once, you will realize that actually you don't have to write this separately. You can write all of these right-hand sides here as a common, like as a one single place. So in practice, I'm not sure if I have it here. Yeah, I do have it here. In practice, what we will do, instead of writing these 3 augmented matrices separately, we will write one single augment. Now it's no longer the augmented in the sense we introduce it, but it will be like the augmented matrix where you see I combine all of the right-hand sides in one place. Here's my A matrix, the one we started with. Here it is. And here's my all left-hand sides, all right-hand sides, all together. We can do this because the set of operations which take this augmented down to this row echelon, this augmented matrix down to this row echelon, and this down to this, we have the same set of operations, this set of operations. And then if we do this set of operations on this long matrix, the result, here we will expect identity, and here we will expect the inverse. In general, for the equations with the inverses, you have to do these row operations now. I have to do it. I will. Once, and I'll show you this to you. So we will just discover this set of operations which will make this reduced row echelon form happening. If you check Moodle, I uploaded another solution helper file for the chapter 4. And all of these routine computations, they present there in full detail. So I will do it now, but for the other ones, if we have to do any other ones, I will refer you to this solution helper file. If you saw that, did you see that? Some of you might probably seen that already. If you haven't, go and check Moodle. But for this one, we will do the operations. You don't have to copy that. It's a long matrices to copy. Like I said, this example in the solution help, I don't remember which one, but it is there. So you don't have to do that. I just show you quickly how the inverse will appear. Look at this.